Okay, so today we will look at the consequences of the second law of thermodynamics now. Let's see. This is a very important topic because we will see that the second law of thermodynamics imposes certain restrictions on the constitutive relations, and unless one obeys those restrictions, we will get anomalous results. So we will study two systems. One is the elasticity system, and the second one is fluid mechanics. Fluid mechanics also, we will not study all kinds of fluids, but only fluids with short-term memory. So those are the two systems that we will consider under this framework here. So let's start with thermoelasticity first. So thermoelasticity. So for this, the constitutive relation is given by xi is equal to xi hat of x comma f comma theta comma g naught. Then t is equal to t hat of x comma f comma theta comma g naught, and then eta is equal to eta hat of x comma f comma theta comma g naught, and q is equal to q naught is equal to q naught hat of x comma f comma theta comma g naught. So now several important points need to be mentioned here. So first is that we are following this principle of equipresence. Okay, so let me just mention this here, equipresence. So whatever kinematical variables we assume for one of the constitutive relations, the same kinematical variables we will assume in all the remaining constitutive relations as well. So you can see that our kinematical list is x, f, theta, g naught, and that list is the same for all the other constitutive relations as well. So this is what we call as the principle of equipresence. Okay, so that means the same kinematical variables are present in all the constitutive relations here. Okay, so the other important thing is that how do we decide this kinematical list? So this kinematical list is based on our experience with that particular kind of material that we are studying. So for the case of elasticity, we know that the stress will depend on the deformation gradient, the temperature, and the temperature gradient. So suppose if you are studying some new kind of material, right, then in that case you would need to know what the kinematical variables are. So if your list of kinematical variables is incomplete, in the sense that you basically let us say that there are certain kinematical variables which are important and you have left them out, suppose, then you will obviously reach to the wrong conclusions about the constitutive relation. So it is very important to have the correct kinematical variables. Now what happens is that typically for some complicated material behavior such as large deformation plasticity or large deformation viscoelasticity and things like that, it is not very clear what the kinematical variables are. Okay, and that is perhaps one of the greatest challenges in continuum mechanics, how to model the constitutive behavior for for complicated situations. So I already mentioned large deformation plasticity, large deformation viscoelasticity, but similarly on the fluid side, non-Newtonian fluids, right? So there also it is not clear exactly what kinematical variables play a role. see, basically the history, of some of the variables will also play a role, right? Such as, for example, in the case of non-Newtonian fluids, a significant part of the history of the deformation gradient will also play a role in influencing the stress. And exactly how much history to take and so on are very difficult issues to resolve, or what kind of functional to take and so on. So basically quantitative modeling is one of the biggest challenges, and as I said that unless you get this kinematical list correct, there is no hope of reaching to the correct conclusions here. But fortunately, let us say that the two systems that we are going to study, that is thermoelasticity and short range memory for the fluids. So essentially Newtonian fluids. So for those, we know that the constitutive relation works. I mean, if you assume this kind of a dependence on the kinematical variables, we know that that works for these two systems. And so this whole procedure is quite successful in finding out the restrictions on the constitutive relations in these two cases that we are studying. But as I've already mentioned, the moment you go to more complicated situations, applying this procedure becomes more and more difficult, because we do not know exactly on which kinematical variables the stress or the entropy should depend on. Okay, so having given this sort of brief introduction, now let us proceed with the application of the second law of thermodynamics to this particular system here. So here your G naught is equal to del x of theta, which is equal to F transpose times G. So G naught is the temperature gradient as defined on the reference configuration. So now with these assumptions, we will find the restrictions in this following theorem. So theorem, a necessary and sufficient condition, necessary and that is really admissible expressed in terms of the free energy. So the necessary and sufficient conditions that every admissible thermodynamic process obey the Clausius-Duhem inequality is that the following conditions hold. So this is one of the restrictions that comes out of the second law of thermodynamics, that the free energy, the first parameter of stress, and the entropy function are independent of the temperature gradient. Then 2 is that T hat of x f theta is equal to rho naught times del xi hat by del f evaluated at x f theta, and eta of x f theta is equal to minus del xi hat by del theta x f theta evaluated at these x f theta. And 3 is that Q naught satisfies the heat conduction inequality Q naught at dot G naught is less than or equal to 0. Okay, so basically the flux is I wouldn't say opposite, but the dot product with the gradient, it's at least not parallel. So it is you can say that the dot product is less than or equal to 0. Yeah. So let us prove this particular theorem here. So the implication of this first statement here, that basically it is independent of G naught. So suppose you were to assume that the free energy is dependent on the temperature gradient, right? Suppose by mistake you take in your constitutive relation that it is a function of the temperature gradient, then the second law would be violated. Okay, and so basically that is the implication of this particular statement here. Okay, so now if you substitute it in the Clausius-German inequality, so then we will get proof. Substituting so this Clausius-German inequality is what I wrote in the statement of the theorem just before I erase that part. So if I substitute it into that, then you will get, and then apply the chain rule. So you will get that del xi at by del f theta g naught minus 1 by rho naught times p hat of f theta g naught times f naught plus del y at by del theta f theta g naught plus theta f theta g naught theta dot plus del xi at del g naught times f theta g naught dot plus 1 by rho naught theta q at naught f theta g naught dot g naught is delta equal to 0. So all I have done is that I have applied the chain rule after substituting the constitutive relation in the Clausius-German inequality. Okay. Now, if you now see these three conditions, right? If you just substitute these three conditions into this particular equation, you will see that these three, this inequality is automatically satisfied, right? Because p hat is del f by del xi by del f. So this part goes to 0. Similarly, this part goes to 0. This part goes to 0. And this inequality is satisfied by this. So automatically you will. So if these conditions are satisfied, then this particular statement is automatically satisfied. So the sufficiency of these conditions is obvious. Correct? So that's so if 1, 2, 3. So that is this statement hold. 1 to 3, if they hold, then so let us call this the star. Then star is automatically satisfied. Automatically. And so, as I said, so that shows that these conditions are sufficient for the Cauchy-Euler inequality to hold. Now we need to prove the necessity of these conditions, and that is the difficult part of this particular proof. So now we need to show that if star holds, then these three conditions are satisfied. Let us try to show that. That is the next step now. Necessity. So the given F diamond G diamond X diamond E diamond then A belonging to length alpha, then alpha belonging to R, and vector A belonging to R3, and there exists an admissible thermodynamic process with F of X diamond P diamond is equal to F and theta of X diamond P diamond is equal to theta diamond G naught of X diamond P diamond is equal to G diamond F dot of X diamond P diamond is equal to A, and theta dot of X diamond P diamond is equal to alpha, and G dot of X diamond P diamond is equal to A. Okay. So basically what we want to show is that suppose if I assume arbitrary values, this is very, very important. So I am assuming that the deformation gradient can assume the arbitrary tensor, of course subject to the usual restriction that the det of f theta should be greater than 0. So if I assume these to be arbitrary with the usual restrictions, of course, then I can achieve those values through an admissible thermodynamic process. See, because so what we are going to do is that we are going to in place of f dot, I will have this arbitrary tensor A, and then I am going to use the arbitrariness of that A to deduce the restrictions on the constitutive relations. But I cannot simply assume something to be arbitrary. I have to show that there exists a thermodynamic process in which these arbitrary values of the variables can be achieved. Okay, so that is what we are trying to construct. So we are trying to construct an admissible thermodynamic process such that these arbitrary values are achieved in that particular process. and then we can use the arbitrary values in this particular statement, then use the arbitrariness of these values to deduce the restrictions of the constitutive relation here. Fine. So, so let us now define these processes. So that this x diamond, p diamond, such that determinant of f diamond plus t minus t diamond times a is greater than 0, and theta diamond plus alpha times t minus t diamond plus g diamond plus t minus t diamond times a dot of x minus x diamond is greater than 0. So basically these are the restrictions. So f diamond, we are assuming that the determinant is greater than 0. Similarly for theta diamond, that is like an absolute temperature, so we are assuming that the absolute temperature is greater than 0. But the perturbation now on this, so the T, if we choose it to be sufficiently close to T delta, then even the determinant of this tensor will also be greater than 0. And similarly, if you choose T to be close to T delta and X close to X delta in some norm sense, then this absolute temperature will also be greater than 0. So these quantities will arise in the admissible process that I am going to construct. So this guy of x comma t is equal to f plus f diamond plus t minus t diamond times a times x minus x diamond, and then theta of x comma t is equal to theta diamond plus alpha times t minus t diamond plus g diamond plus t minus t diamond times a dot x minus x diamond. So now you will see that this particular process gives exactly these variables. Okay, so let us see. So suppose if you find out what is the absolute temperature at x diamond, t diamond. Okay, this part will go to 0 because you are evaluating at t equal to t diamond. Then similarly, this part will also go to 0 because you are evaluating it at x equal to x diamond. So you will get theta at x diamond, t diamond is equal to theta diamond. So that is exactly this particular state. Then if you take the deformation gradient of this particular process, that will be this particular tensor, and if you evaluate it at t equal to t delta, you will get f delta. That is this particular statement, and so on. Okay, so if you now find these various quantities for these two processes, then you will get these arbitrary variables. And it is an admissible thermodynamic process. So what do we mean by admissible thermodynamic process? That means it satisfies the condition that the absolute temperature should be greater than 0. So that's what is written here, right? This whole thing, whatever is the absolute temperature, that is greater than 0 because we can choose T to be sufficiently close to T diamond and X to be sufficiently close to X diamond such that this is greater than 0. And similarly, the determinant of the deformation gradient, which is this particular term, so that is also greater than 0. So to summarize now, what we have done is that we have constructed an admissible thermodynamic process which gives us arbitrary values of the deformation gradient, the absolute temperature, the temperature gradient, the rate of the deformation gradient f dot, theta dot and g dot. Okay. Of course, subject to the restriction that determinant of f delta f diamond should be greater than 0 and theta diamond should be greater than 0. So apart from those usual restrictions, other than those usual restrictions, these things are completely arbitrary. And we'll use this arbitrariness, as I said, in proving these restrictions on the constitutive relations now. Okay, so if we now apply if we write the second law of thermodynamics for this particular admissible process, then let us see what we get now. So we'll get now del xi by del f evaluated at f diamond. Now, so we now everything is evaluated at f diamond, theta diamond, g diamond, which is this process here, times a, for a, because f dot is now a. So I'm just substituting f dot for f dot in this particular thing, plus del xi hat by del theta f diamond, theta diamond, g diamond, plus theta hat of f diamond, theta diamond, g diamond times alpha plus del xi hat by del g naught f diamond, theta diamond, g diamond dot a plus 1 by rho naught theta diamond q hat naught f diamond, theta diamond, g diamond dot g diamond is less than or equal to 0. So now we are applying the Clausius-Duhem inequality to this particular process that we have constructed, and so we have now got arbitrary values here. So this a is arbitrary, this small a is arbitrary, this alpha is arbitrary, and this g delta is arbitrary. Okay, and now we will use this arbitrariness in order to show the conclusions in the theorem. So we can write this particular statement as del xi hat by del g naught of f diamond, theta diamond, g diamond plus f1 times f diamond, theta diamond, g diamond, a and alpha is less than or equal to 0. Right? So basically so what I am doing is that this term I am writing it here, and then all the remaining terms, that is just some function of these variables here. Sorry, this should be a dot a here plus this f1, right? And now we can see that this list does not have this a here. Okay, so we'll fix these values. So fix f diamond, theta diamond, g diamond, a and alpha. Then this is just some constant value. Okay, and then I can use the arbitrariness of a. So you can switch the sign, for example, of a and choose it to be of such a magnitude that it overpowers this particular term, and you will see that this whole thing is always violated unless this term is equal to 0. So you can put in numerical values and convince yourself of this. So this is valid for all a basically. Okay, so let us first write this. So fix f diamond, theta diamond, g diamond, a and alpha. Okay, so then this f1 of f diamond, theta diamond, g diamond, a alpha is equal to some constant, right? And so basically let us call it as equal to c. Then what we'll get is that del xi hat by del g naught evaluated at f diamond, theta diamond, g diamond dot a plus c is less than or equal to 0. Right? So so this part here plus this is now some constant c. So that is what I am writing. And then, as I said, that you can convince yourself that this is valid for all a. So you are allowed to switch the sign on a. So suppose even if this inequality is satisfied, you are allowed to switch the sign on a. So let this whole term dominate this term in terms of magnitude, and then switch the sign. So then this inequality will get violated unless this is equal to 0. Right? So that's why. So we are using the arbitrariness of a in order to show that this particular term is 0. So the conclusion that we can draw now is that the free energy is independent of the temperature gradient here. Okay, so this implies, so this is not like this. So this implies that del psi hat by del G naught evaluated at f theta G diamond is equal to 0. Okay. So that's the conclusion that we get here. Fine. Okay. So then now let us go to the next thing. So let me erase this particular part here. So now actually in this particular statement, this part is gone, right? Because that is now 0. So now do the same thing now. Basically now for this particular term here. So let us write that. So you will now get del psi hat by del theta. Then this is again evaluated at f theta G diamond. Actually now we don't need to put the G diamond because we have already shown that it is independent of G diamond, but let us just keep it there. Then this is f theta G diamond times alpha plus f2 now of f diamond theta diamond G diamond and A should be less than or equal to 0 now. So here again now you fix f theta G and A. Okay, so fix f theta G A. Okay, and so this particular thing is a constant. So what you'll get now is that del psi hat by del theta evaluated at f theta G plus eta f theta G times alpha plus now some constant, so that is plus some C tilde is less than or equal to 0. So this is some constant now, right? Because you are fixing these things, so this whole thing is a constant. Now this is valid for all alpha. Again, let this particular term dominate this particular term in terms of the magnitude, and then you can switch the sign on alpha because alpha is arbitrary, and so what you will get is that this bracketed term should be equal to 0. Okay, so from this you will get that. So from this you will now get. So this implies that eta hat is equal to minus del psi by del theta evaluated at f theta, because we have already shown that it cannot depend on G diamond, and so even this derivative will be independent of G diamond. So the entropy function will also be independent of the temperature gradient. So that is what now we have shown here, and so now you can follow the same procedure and prove the remaining things in the theorem basically. So for example, the let us see, so you will get, I think I missed out something here. So here, I'm sorry I missed out here, this should have been minus 1 by rho naught of T hat of F diamond, theta diamond, G diamond. Okay, so please correct this statement here. So here then what you will get is that T hat is equal to rho naught times del psi by del F of F theta, and so we have already shown that it cannot depend on G diamond. So the first theorem of stress also cannot depend on the temperature gradient. Okay, so as a so that is one of the restrictions of the second law of thermodynamics. So that then finally leaves only, so all the remaining terms. So this term now goes to 0. This term goes to 0. So the only term, so this term has already gone to 0. So the only term that is left is now this particular term, and so we will get that Q naught times G naught is less than or equal to 0. So that was the third statement in the statement of the proof. So this shows the necessity also of all the three statements that are given in the proof. So to summarize, basically what we have shown is that as a consequence of the second law of thermodynamics, we have shown that the free energy function, the first theoretical law of stress and the entropy functional, they cannot depend on the temperature gradient, and in addition the temperature gradient and the heat flux satisfy this particular inequality, that is this as a consequence of the second law of thermodynamics here. Okay, so having proved this particular theorem, now let us move on to the conclusions that follow now from adopting these restrictions on the constitutive relations. So now by applying the chain rule, we will get that xi dot. So now we have seen that xi is equal to some xi hat of x comma f comma theta, because it doesn't depend on the temperature gradient. So this is the relation here. So I will get that this is equal to so if I now write this as del xi by del f times f dot, so this is del xi by del f times f dot plus del xi by del theta times theta dot, and then we have seen that the del xi by del f is equal to 1 by rho naught times t times f dot plus this is minus theta, so this is minus eta times theta dot. So xi dot will be given by this particular statement, and then we can substitute this now into the second law of thermodynamics. So that is del eta naught by del t is 1 by theta naught times qh naught minus 1 by rho naught del h dot q naught plus 1 by rho naught times t times f dot minus eta naught minus xi dot naught. So this actually is the energy equation, actually not the second law of thermodynamics, sorry. This is the energy equation expressed in terms of the entropy. So we had one expression of the energy equation in terms of the internal energy, and this was the statement of the energy equation in terms of the entropy function. Okay, and so now if you substitute this, so you can see that this particular part is going to go to 0, because xi dot is equal to 1 by rho naught times tf dot minus theta naught. So this will go to 0 here, and so what you will get is that you will get that rho naught times theta times del eta naught by del t, keeping x fixed, is equal to rho naught times qh naught minus del dot q naught. Okay, so that is the conclusion that you will get in this particular case here. So so basically what it shows is that an admissible thermodynamic process in a thermoelastic material is adiabatic if and only if it is isentropic. Okay, so that is what it shows. So isentropic means that there is no change in entropy, that means this left hand side is 0, and adiabatic is if adiabatic process we define if there is no heat input and there is no heat flux in the system, then basically this part is going to go to 0. So a process is adiabatic, that means means this part is 0 if and only if it is isentropic. That means the entropy remains a constant. So basically what we are saying is that there is no internal dissipation. So if you are familiar with fluid mechanics, if there is viscosity in the fluid, then there is something known as viscous dissipation. So that is like a friction which generates heat, and so that actually adds to the entropy, right? That generates entropy. But in the thermoelastic process, there is nothing like this internal dissipation, and so if you don't supply any heat and there is no heat flux, then basically the entropy just remains a constant. Okay, so that is the conclusion from this. So does an admissible thermodynamic process in a thermoelastic material is adiabatic. That means rho naught QH naught minus del dot Q naught is equal to 0. If and only if it is isentropic, and only if it is isentropic. As I said, basically eta dot is 0. So basically it means that there is no internal dissipation. But so suppose if you go to something like viscoelasticity, okay, then there will be an internal dissipation and so on. So here we are neglecting those viscous kind of effects, and so in this particular case we get this conclusion here. So there is no dissipation basically. Let me put that. So no dissipation. Okay. So that is the important thing in a thermoelastic process. Okay, so okay, then the conclusions, whatever we have drawn, were without any constraints. So now let us look at certain constraints. Okay, so suppose so these are certain kinematical constraints now that we are going to look at. So for example, one of the kinematical constraints that we have looked at already is incompressibility, correct? And so suppose now if the thermoelastic material is incompressible, then what effect does it have on the constitutive relation? So that is what we want to now examine. So we have already seen that the constitutive relation in that particular case can be written as minus p of x comma t times identity plus some beta minus 1 beta inverse plus beta 1 times p. So p is the left Cauchy-Green strain tensor, tau is the Cauchy stress, and we saw that for an incompressible material, this part here is constitutively indeterminate, right? So that I am now going to prove that using this second law of thermodynamics. So at that time I just stated this particular result without having proved it. So now we will show that this particular part is constitutively indeterminate. But of course it can be determined using the balance of linear momentum and the appropriate boundary conditions. But given B, you cannot find out P of x comma t. So that is the effect of having a constraint like an incompressibility constraint. So let us look at how to derive that now. Look at this now. So suppose if you have an internal constraint, so this is we'll call it as internal constraint. By internal we mean that the nature of the material is that. So by an external constraint, suppose if you put roller supports on a structure, that I would call as an external constraint. This is an internal constraint in the sense that the nature of the material is such that these constraints. So, for example, the rubber type materials are almost incompressible, right? And so that is an internal constraint. That is not an external constraint that we are putting on the structure, such as roller supports or things like that. So here these internal constraints, let us consider them in the form of mu1f is equal to 0 and mu2 of theta naught is equal to 0. So let us consider the constraints to be of this particular type. So if you apply the chain rule here, then you will get del mu1 by del f times f dot is equal to 0. And here you will get del mu2 by del theta naught times theta naught dot is equal to 0. So these are the constraint equations that we will get. And now you will have to modify the statement of the Clausius-Duhem inequality. So let us look at that. So now in place of whatever I had earlier, now I will get this particular thing. So this is f theta naught g naught plus minus 1 by rho naught times t hat of f theta naught g naught plus lambda 1 by rho naught del mu 1 by del f times f dot plus del by del theta naught of di hat f theta naught g naught plus theta hat of f theta naught g naught plus lambda 2 del mu 2 by del theta naught times theta dot naught plus del psi by del g naught times f theta g naught plus 1 by rho naught theta naught 1 by rho naught theta naught times q hat naught of f theta g naught dot g naught is less than or equal to 0. Okay, so now this lambda 1 can be an arbitrary scalar because del mu 1 by del f times f dot is 0. Right? So that's why we can have this lambda 1 as an arbitrary scalar. Similarly, this lambda 2 is also an arbitrary scalar because essentially we are just adding 0 to that particular statement. Right? So this is the addition of a 0 and this is also an addition of a 0 to that particular statement. But it affects now. So now we again go through the same procedure as we went through while reducing the restrictions on the constitutive relation. So what we will get is that we will get that t hat of x f theta naught is equal to rho naught times del psi hat by del f, and is x f theta naught plus lambda 1 times del mu 1 by del f. Okay, so this is the conclusion that you will get now. That so this term now gets added. So previously, so if the constraint had not been there, then we do not have this particular statement. But this term. But now this term gets added to the expression for the stress. Similarly, for the eta also one term gets added. So that is x f theta naught is equal to minus del psi hat by del theta naught of x f theta naught minus lambda 2 times del mu 2 by del theta naught. And so now you can see that basically this indeterminate part is now coming because of this particular term that is getting added. See, if the constraint had not been there, then we would have got beta naught of I, where beta naught would be a function of the principal invariance of B, correct? But now, because of this particular term, in the presence of incompressibility, you will get this particular term. So we will see that. But before that, let us just define certain terms here. So this n let us call this n, which is lambda 1 del mu 1 by del f. This is called as a reaction stress. So basically, just like if you have a roller support on a structure, then that roller support will exert a reaction, right, to the load on the structure. So in the same way, this stress is like a reaction to the internal constraint that you are imposing, that the material is imposing. So that is the reason that it is called. So exactly analogous to an external constraint, you can think of this as an internal now reaction to the constraint that you are imposing, and so this is known as reaction stress here. And the corresponding, so this is the reaction stress for the first order of stress. Similarly, then you can deduce what is the reaction stress now for the Cauchy stress. So use the relation that T times F transpose by J. Use that particular relation to find out what is the reaction stress for the Cauchy stress now in that case. So there is a here, so for the n, so let us call it as n tau. So that is equal to n times F transpose divided by J, and then that will be equal to lambda 1 by J times del mu 1 by del F times F transpose. So this is the reaction stress now for the Cauchy stress. Okay, so first we deduce what is the reaction stress for the first order of stress, and then from that this n tau, because tau is the Cauchy stress, so that is the reaction stress now for the Cauchy stress here. Fine, and so let us take an example here, but before that, okay, let me just, so suppose if there now I have considered only one constraint. If there are multiple constraints, then let us look at what happens. So it's a fairly straightforward extension for multiple constraints. So if you have so multiple constraints now, so if you have mu I of f is equal to 0, so this is I equal to 1, 2, okay. So then in that case, the reaction stress will be n will be summation I equal to 1 to n of lambda I times del mu I by del f. So just basically it will be a summation of all the individual reaction stresses here. Okay, fine. So let us take an example now to illustrate this whole reaction stress now. Yes. So if we take the constraint of incompressibility, so this is example. So you are having mu of f is equal to determinant of f minus 1. So recall that if it is an incompressible material, then it can only undergo isochoric motions, right? And that is a volume preserving deformation. So you will get that determinant f is equal to 1 in that particular case. So this mu of f, which is determinant of f minus 1, that is equal to 0. So from this, what you will get is that if you now differentiate this, so you will get that the reaction stress will be equal to lambda 1 times cofactor of f. And then from this, what you will get is that n tau. Now this will imply that n tau, so that is just multiply this cofactor f by f transpose and divide it by j. But j is equal to 1. So what you will get is that you will get that this is equal to lambda 1 times I, and this we call as minus p of I. So this lambda 1 is arbitrary. And so this p also is an arbitrary tensor. And so this is just it's just a function of x comma t basically. So this you can now add this reaction stress to the usual stress. So originally we had beta naught of the principal invariance of identity plus beta 1 of the invariance of B times B plus beta minus 1 invariance of B times B inverse, right? And now this gets added, so minus P of x comma t times identity. And so because this is arbitrary anyway, so this is determinate, but this is indeterminate. So once you add this, there is no point in considering this. So in general, we can just think about it as this is the constitutive relation now. Okay, so that is how the minus P of x comma t times I appears in the constitutive relation for an incompressible material. So that is basically a reaction to the internal constraint. And then in a similar way, you can deduce the appropriate restrictions if you have constraints on the temperature, for example. So I will not go into that, but one can deduce it. So one interesting case is that if the body is rigid, then in that case, actually all the components of the determinant gradient, deformation gradient are constrained, because then in that particular case, your F has to be equal to Q, which belongs to our class, right? So all the components are restricted, and so the entire stress tensor in a rigid body is constitutively indeterminate. Of course, so we are not saying that there is no stress. Okay, we are not saying that the stress is zero. All we are saying is that in a rigid body, it is constitutively indeterminate. That means you have to determine the stress by using the balance of linear momentum and the boundary conditions. Okay, so that is the way. So in a completely rigid body, the entire stress tensor would be constitutively indeterminate. So anyway, so this is something about how to handle internal constraints within a system. Now we will also use the axiom of material frame indifference. So basically, so far we have only used the second law of thermodynamics. We have not used the axiom of material frame indifference. And so now let us impose material frame indifference on the constitutive relation and see what we get. So we are always allowed to do that, because as I said, that we are adopting that as an axiom, right? So that means like a principle, and so we are allowed to do that. So now MFR, so that is what now let us consider. So the restrictions imposed by material frame indifference. So here first let us note that Q naught of star is equal to J star times F inverse star times Q star, which is equal to J times F inverse times Q transpose times Q times Q, which is equal to J times F inverse times Q, which is equal to Q naught. And so the Q naught star, that is the flux, heat flux as observed by the star observer, is the same as the heat flux as observed by the unstarred observer. And again, this situation is exactly analogous to the second Kirchhoff stress. So the same second Kirchhoff stress is observed by both the observers. So that is because it is totally defined. All this quantity is totally defined on the reference configuration, and we have seen that the same reference configuration is observed by both the observers. And so this conclusion is not at all surprising. Just as I said, the situation is exactly analogous to that for the second Kirchhoff stress. And then similarly, you have G naught star is equal to del x of theta star, that is equal to G naught. Okay, so this the temperature gradient is also the same as seen by both the observers here. Fine. Now let us impose material frame indifference. So we will get that psi hat of f comma theta is equal to psi hat of q times f comma theta. Right. So that is the two different observers. So we have seen that f star is equal to qf, and the same free energy, because free energy is a physical variable, and so the same free energy is observed by both the observers. So you will get this particular thing. And similarly, t hat of f comma theta is equal to q transpose times t hat of qf comma theta. So this is the restriction on the first order of stress, and then the restriction on the second, the entropy. So that is equal to theta hat of qf comma theta and q hat naught of f theta g naught is equal to q hat naught of qf comma theta comma g. So now these are the restrictions that are imposed by the principle of material framing difference. So we have already incorporated the restrictions imposed by the second law of thermodynamics. So for example, we are now no longer assuming that the psi depends on g naught, right? So that we have already shown that the free energy, the entropy function, and the first of stress cannot depend on the gradient, temperature gradient, and so that conclusion we have already incorporated in these constitutive relations. So now we are simply applying the principle of material framing difference to these particular things. So if you now choose, okay, so choose Q to be equal to R transpose, right? And so this R is the R that occurs in the polar decomposition of the deformation gradient here. So if you choose that, then what you will get is that psi is equal to some psi hat of u comma theta now. So these are now the conclusions. So basically the dependence on f now reduces to a dependence on u, right, which is the stretch tensor. And similarly you will get T is equal to f times u inverse times T hat of u theta, and eta is equal to eta hat of u comma theta, and q naught is equal to q hat naught of u comma theta comma g. So what we have shown is that basically the dependence on f now goes to a dependence on u. And so basically that goes to a dependence on c, because u is square root of c, or in other words, c is again linked to e, which is the green Lagrange train. So ultimately we can say that the dependence on f reduces to a dependence on the strain, that is the green Lagrange train. Okay, so that is what we have now shown here. So let us write that now. Okay, so effectively now what we have is the following. So effectively now, since u is equal to square root of f transpose f, which is equal to square root of c, and E is equal to half of C minus I, or C is equal to 2E plus identity. So that is why basically it depends on the E. So we now have that psi hat of x comma f comma theta is equal to some psi tilde of x comma E. So the important thing now that comes out of material framing difference is that the dependence on f reduces to a dependence on the green Lagrange train, the E. Okay, so that is one of the most important conclusions from this particular exercise here. Okay, so with this, then we will be able to prove now the following theorem here. So let us prove this theorem. Given last material with free energy line tilde of x comma e comma theta, the principle of MFI. Is satisfied. If S of x e theta is equal to rho naught of del xi by del e of x e theta and eta tilde of x e theta is minus del xi by del theta of x e theta. Okay, so this is it. So basically the second theorem of stress is given by the gradient of the free energy with respect to the green strain here. So let us show that. So proof. So this is just actually the proof is just an application of the chain rule here. So del xi by del f theta in the direction u is d of f xi tilde of f comma theta in the direction of u. So this is just the definition of the gradient with respect to f. So this is nothing but the first theorem of stress. Okay, so that's basically we are writing this in terms of the directional derivative. So this is df of xi tilde of e comma theta. So this is the chain rule. So this is in the direction of u. So this is equal to d of e in the of xi tilde in the direction of d of f of e in the direction. So this is nothing but the chain rule. We are applying the chain rule here, and this quantity let's use the fact that E is equal to half of F transpose F minus identity. So you can find the directional derivative of this with respect to F. So this is equal to half of D of E of xi tilde of E comma theta in the direction of F transpose U plus U transpose F. Okay, so this is the directional derivative. And now express this in terms of the gradient here. So let's do that here. So you will get, so from here, from here, what you will get is that this is equal to half of del xi tilde by del E of E comma theta times F transpose, this is matrix in our product, F transpose U plus U transpose F. Okay, and this I can write as equal to F by 2 times del xi tilde by del E of E comma theta plus del xi tilde by del E evaluated at E theta transpose. This is transpose from the whole thing times U. So this is the usual trick. So basically we are writing A, B, C is B transpose A matrix inner product C, and so these kind of properties we have already seen. So I'm just using those properties in order to go from this step to this particular step here. And then del xi by del E is a symmetric tensor because E is symmetric. And so this will just be the same term actually. So let us simplify this expression here. Then what you will get is, so this is equal to now F times del xi by del E matrix inner product E. Okay, so basically now what we have shown is that T hat of f theta is equal to rho naught times del xi hat by del f times f theta. So that is equal to rho naught of f times del xi tilde by del e times e theta. That is because we have shown that del xi by del f is equal to f times del xi by del e, right? And so that's the reason that we can now write it in this particular way. And then after this implies that S is equal to, so T is equal to Fs, so this is F inverse of T, so that will give me rho naught times del xi tilde by del E of E comma F. So that is exactly this particular expression here that I had written here. So this is the this expression. So we have now been able to derive this. And the entropy thing is just that is just the derivative with respect to theta will remain the same. Whether this argument is based on f or e, it doesn't matter. So that partial derivative with respect to theta will remain the same here. So so the other conclusion will just follow. So since so let us just write it here. So since xi hat of x comma f comma theta is equal to xi tilde of x comma e comma theta, you will get this particular relationship for the e time. Okay. So to conclude now, so let us just summarize the whole situation now. So now a summary, just to summarize the entire discussion now. So summary is that so as a consequence, right? Consequence of the second law, right? Second law and MFI, we now have that S tilde of E theta is equal to rho naught del xi tilde by del E. This is a function of E comma theta. So it is not a function of the temperature gradient. That is one main thing here. So it's a function only of E and theta, and it's a gradient of the free energy with respect to the Green strain tensor, and your eta tilde, which is E comma theta, that is equal to minus of del xi tilde by del theta of E comma theta. So those are the conclusions from this. So you can see that this is very similar to the constitutive relation for a hyperelastic material, right? Where we have assumed that we said that S is del W by del E. So this is very similar to that. And in fact, so when the if we take the process to be isothermal, then in that particular case, you can take the theta to be a constant, right? And in that case, this will be exactly identical to the strain energy density. If I take rho naught times xi tilde to be the strain energy density function, then you will get the second Pioneer cos stress as a gradient of the strain energy density function if it is an isothermal process. Similarly, for an isentropic process also, we can show that there exists a strain energy density function. So basically, we will look at that. We will look at this aspect in greater detail in the next class. But for now, what I will say is that this provides a justification for assuming that a material is hyperelastic, right? So this is a thermodynamic justification for assuming that a material, as I said, that typically whenever we assume that a material is elastic, automatically we also assume that it is hyperelastic. And so this relation here provides a justification for why we can take a material to be hyperelastic. So at least in the isothermal case, we can definitely take it to be hyperelastic, and the same way even for an isentropic process also we can take it to be hyperelastic. But typically even if it is a function of theta, typically even then also we will assume that the case of hyperelasticity. So we will anyway discuss these aspects in greater detail in the next class.